Hello there guys, welcome back to another epic and extra maths video. In this video we're once again looking at the ratio test. We have another absolute monster on our hands causing a ruckus. Let's see if we can absolutely destroy this guy. So, does the sum from t equals 1 to infinity of t factorial cubed divided by 3t factorial converge or diverge? We're going to use the ratio test. By now, I hope that you are very, very, very happy with this. I'm not going to go through the inconvenience of explaining all of this once again. I think we all are very happy with the ratio test, or how it works at least. We're here to tackle this absolute demon. So let's just go straight into it. One difference, by the way, here is that we're using t instead of n, but of course it makes no difference. So let's take the limit as this time it's t approaches infinity of the ratio between the t plus 1th term and the tth term. So what have we got here? Well, the t plus 1th term would be t plus 1 factorial and then cubed divided by 3 times t plus 1 factorial. And then that gets divided by the tth term. So t factorial cubed divided by 3t factorial. Okay, hopefully that makes sense. Once again, we have a pretty grim fraction to deal with, but that should be no issue for us at this point. We know how to deal with fractions, of course. So we take the limit as t approaches infinity, and what do? Well, we float the 3t factorial up to the very top, and we float the 3 times t plus 1 factorial down here. So we have a slightly more normal fraction, even though it's still complicated, which is t plus 1 factorial cubed times 3t factorial divided by, and this here, this 3 times t plus 1 factorial, I'm going to write this as what it is, which is 3t plus 3 factorial. And then we have got the t factorial cubed, which is this term here. Okay, I'm going to move out of the way. Make sure that you're really super duper happy with that before I move on. I'm just going to make this slightly shorter just so we can have a bit of space. And can we cancel out anything? Immediately, it doesn't look like we can, but in a second we will be able to. We're going to do one more line of simplifying before we try and cancel anything out. Okay, so here's my thinking, okay? I'm thinking we have a 3t plus 3 factorial, and we have a 3t factorial. Something is going to simplify there. I'm also thinking we have a t plus 1 factorial cubed and a t factorial cubed. So I'm thinking something is going to simplify there as well. And of course, yes it is. So the t plus 1 factorial, first of all, I want to have that in terms of just t factorial so that I can try and cancel it out with this. So I'm going to write t plus 1 factorial as t plus 1 times t factorial. But remember, the whole thing is still being raised to the power of 3. It's still being cubed. And then it's still got the 3t factorial timesing by it. Okay, and then the denominator, I'm going to do one thing here as well. I'm going to write 3t plus 3 factorial as 3t plus 3 times 3t plus 2 times 3t plus 1 times 3t times 3t minus 1. But all of those terms, they're just wrapped up in 3t factorial, okay? And then there's also the t factorial cubed as well. T factorial cubed. Okay, so for a second it's looking more complicated, but it's going to become simple very quickly. So is there anything that we can immediately cancel out? Well, yes, 3t factorial and 3t factorial, they're gone. Lovely. Okay, we're making progress already. Now, I'm going to go on to the second board here just to have a bit of space. Now, I'm noticing that we can distribute this power of 3 to the t plus 1 and the t factorial, and when we do that, it will cancel out with the t factorial cubed down there. So let's do that. So now I've got the limit as t approaches infinity of the absolute value of, and I'm going to write this as t plus 1 cubed times t factorial cubed. Okay, that's the numerator. The denominator is still pretty grim. It's 3t plus 3, 3t plus 2, 3t plus 1, and then t factorial cubed. Okay, so still not great, but what can we do? We can continue to simplify it. I think that my red chalk, there it is, it's hiding. It was harboring enemies of the state. Okay, and yeah, what can we do? We can keep simplifying. So t factorial cubed, goodbye, goodbye. Okay, so what do we have? Well, now we just have a big polynomial thing. So we have the limit, and this is definitely the, we're in the end game now, I would say, as Dr. Strange would say. And so let's expand this out. T plus 1 cubed, I'm going to use the binomial expansion in my head right now, and I'm going to go, this is t cubed plus 3t squared plus 3t plus 1. Okay. And then this is slightly more complicated because it's not the binomial expansion, it's just something else. So of course we could just expand it all out. What I'm going to do though is, and I kind of alluded to this idea in the last video, I'm only going to look at the leading coefficient term for a second. So to get the highest power of t, that would be t cubed, because there's 3 linear terms here. It would be 3t times 3t times 3t. That would be 27t cubed. So we have 27t cubed. Now, technically, there is no reason why I couldn't just go ahead and expand the whole thing out, but it would just be a bit time consuming, and I don't want to waste you guys' time. So just stay with me for a moment. I'm just going to say I don't actually care what any of the other terms are. So I'm just going to say that whatever the t squared term is, I'll just call that a, so at squared, and then bt, so whatever the numbers that have just a t in them add up to, I'll just say it's b, and then plus c. So a, b, and c are numbers that I could just work out, but I'm making the point that it would just be a waste of time because it's actually irrelevant what these numbers are, and I'll go into a bit more detail in a second on that. Okay, so just to save time, because it's really boring to obviously do that, and we don't need to. So why would we? It's all about efficiency. Okay, I'm like the maths version of Doge. I am the Department of Mathematical Efficiency, guys. Okay, right, now what do we do here? Well, it's a cubic divided by a cubic. So many of you will be very happy to just say that this limit is 1 divided by 27. That is what it is. But if we want to go there and use L'Hopital's rule, we can. So using L'Hopital's rule, just to confirm that's true, maybe, then we just do L'Hopital's rule by differentiating the numerator and denominator of this fraction because it's infinity divided by infinity. Okay, and then 27 times 3 would be 81, so 81t squared. This would be 2at plus b, okay. We still need to use L'Hopital's rule here because it's still infinity divided by infinity. So the limit as t approaches infinity of, okay, what will we have here? We'll have 6t plus 6 divided by 81 times 2, that would be 162 times t plus 2a. Okay, it's still infinity divided by infinity. So one more time, the limit as t approaches infinity of 6 over 162. Okay, and of course this is just equal to 6 over 162, but 6 over 162, if we divide both sides by 2, top and bottom by 2, we will get 3 over 81, and 3 over 81, remember 81 is 3 to the power of 4, so this is basically 3 to the power of minus 3 if you simplify it, and you do get 1 over 27 as we originally thought. You do get 1 over 27. Hopefully you can see that okay. Now obviously 1 over 27 is, I'm going to write it down even though it's really obvious, it's less than 1. Of course it is, it's a 27th. So what does that mean, guys? Well, because the ratio is less than 1, it converges. So this is a convergent, and I'm looking for my red chalk once again. There you are, my best friend. This also converges. Yes, it does. Convergent, converges. And that's it. So once again, I'm going to let you have a little look at that, make sure you're really happy with what we did. I know it's a pretty long question. It was an absolute beast, wasn't it? But I think that we did a good job with it, and there's the other page if you want to see. So only the beginning is really anything new. If you've already seen L'Hopital's rule, if you already know how to simplify a fraction, is there anything really new here? Well, kind of not really, but still very satisfying, right? I think so. As always, guys, thank you so much for watching. I highly appreciate it, and I'll see you in the next video. Cheers.